Welcome back, engineers. We are discussing common techniques and algorithms in system design, and I know that some of you have been requesting for code implementations of some of these topics. So I hear you. Just stay with me. I just want to cover a few more topics, which will try to understand why and how these things work, and then code implementations really become simple, right? So I hear you. Just stay with me. I'm going to give you the code implementation soon, right? So in this video, let's talk about tries. I hope you're ready. Let's get started. So when we do any type of search in some popular apps like Google, as we type searching, we get some suggestions, right? So these are search autocomplete suggestions. So this we can see in Google. This we can also see in apps like Amazon when we're searching for any type of product, let's say like books. As we keep typing, we get all the different types of suggestions. And also when we are trying to look up for some word in, say, some web dictionary, right? So we are trying to search for some string and we get some suggestions, and even after searching we get immediate lookup, right? So in these type of situations we can think about using tries. So trie is a fantastic data structure that will simplify lookup to a great extent, right? So let's see how a trie data structure is built, right? So let's see how to build a trie, and let's see how to insert some stuff. So on the technical side, a trie node would look something like this. It has a class trie node and it has children of itself. So this is typical in any tree type of data structures. There's a node and it is connected to several other nodes, right? In this case, if we are building an English word trie, we are going to have a maximum of 26 children, one for each character of the English alphabet, right? And then we're going to have a boolean to mark if this current node is the end of any word, right? So let's see how we can build this. Let's say we are trying to insert cat into our trie data structure. So this is how it goes. So we start at the root node. There is no data in this. It just have pointers to 26 other child nodes, right? So when we want to insert something like a cat, we want to know at which index among these 25 children we want to put this cat, right? So for this, we're going to make use of simple ASCII calculations. We just do C minus A, right? And the ASCII difference, the distance between these two will come out to be 2, right? Because the distance between A to C is 2. So we go to 2 and then we insert C here, right? And C itself will have 26 of its own children, and then we go to the next character. We are done with C, we go to A. Now what is the difference between A minus A? This is 0. So we go to 0 and we insert A. Similarly, we go to number 19 and we insert T, right? Now we have reached the end of the word, and at this point we can mark this one as end of word to be true. So the green bubble indicates that it is end of word. So I'll just erase this one so that there is no confusion, right? So all the green bubbles are end of words. Similarly, if you want to insert a car, we do the same procedure. We take the difference between C minus A, we go to 2. At 2 we already have C, and then we go to A, we already have A, and now we need the distance between A minus R, which will come out to be 17. So we insert R and we mark it with end of word green, right? Now similarly, let's try to insert the word dog. So what is the distance between D and A? It is 3. So we insert a D here. Let me take white. So we insert a D here, and then we need the difference between O and A, and that difference would be coming out to be 14. So D will also have its own children, and at the 14th index we are going to have O, and O will have its own children, and at some point we will have G. I think the difference between A and G will be somewhere around 6, right? So we have G here, and this is the end of the word, so we'll mark it with a green bubble, right? So we have inserted dog successfully. And if we want to insert a bigger word like doggy, we will do the same procedure. We already have dog, and we add G and Y to the children of G. So this is how we can insert any word into the trie data structure, right? So what will be the time complexity? Time complexity is O of L, L being the length of the word. So depending on the length of the word, we go deeper and deeper into the tree, and that is how we can insert any type of word, right? Now let's see how search works. Let's say we are searching for the word cat, right? So how do we search? Similar to insert, we go character by character. First we take C, we take the difference between C minus A, we get the number 2. So we start at 2 from the root node, and then we go to C, and from C we take the second character, which is A, we do A minus A, we get 0, and then we go to A, and then from there we go to T, which is at number 19. So when we have reached the end of the character, this is where we check if this particular node is having the boolean flag is end of word icked or not, right? If it is true, then that is a valid word in our trie data structure. Otherwise, we return false, right? Similarly, if you want to search for the word cart, which is not there, let's see how that goes like. So we start at C, we go to A, and then we go to R by doing C minus R, and then we want to do T here. Now T is available as a sibling to this one, but we need R as a child to this one, right? We needed something here. So since we have reached R and it has no children, we can conclude that this word does not exist in our trie data structure, and we can return it or insert it or whatever we want to do it, right? So what is the time complexity for this one? Again, it is O of L, L being the length of the word. We go deeper and deeper as many times as the length of the word. So this is how simple search and insert works, but what we are really interested in understanding how search autocomplete works, right? So let's see how that looks like. So this is how autocomplete works. So let's say we want to get words with prefix CA, right? So this is basically prefix search. So as we are typing, we are giving it some prefix to work with, and depending on the prefix, it is able to give out the future words, right, in a predictive format. So this is how it looks like. So we're going to add one more thing to our trinode data structure. We're going to add frequency to this because we want to get the most popular words as search suggestions, right? We don't want to be getting random words as suggestions. We want it to be popular searches, and we want it to be updated as frequently as possible so that more and more people search. Let's say for a trending topic, I want those to be at the top of the suggestions. That's the idea behind search autocomplete anyways, right? So let's see how this goes like. So we're going to maintain a frequency counter per node. So here is what we'll do. So we had inserted the words cat and car previously, right? Now what we'll do is when we are inserting, we put the frequency as 1 because somebody has actually inserted it, which means maybe somebody has searched for it, right? So whenever there is a new search coming for this word, we increment this counter and make it to 2. Whenever somebody is searching for a car, we increment this one and make it a 2, and so on, right? So this way we are going to maintain frequency at every node. So let's say we have done our trie data structure, and currently the frequency stands at 5,7 at car and cat, right? So here is how we get words with a prefix CA. So when somebody is searching for the words with prefix CA, we go down the tree, we reach C, we reach A, and then we look at the children and whatever are the finished words from here on. So we're going to do depth first traversal in this case. So we're going to start at this level and see that whatever are the finished words. Let's say our finished words are car and cat. And let's say there are other words like this. Maybe there is another word T, making it CART, cart, and that is also a finished word. Let's say that is also having a frequency counter of 2, let's say, right? So all of these are given as part of the output. So we're going to take all the completed words. So we are looking for the boolean flag true in all of these nodes, and we're going to get all of these words out. So this is what we got. We got car at 7, we got cat at 5, and let's say we got cart at 2. Let's say we have these 3 words. So what we'll do is we will sort them based on descending order. So in this case it is already sorted, but we will naturally do a sorting order, and we will return the top K words. Top K being whatever is the suggestions that we want to give out. Let's say in this case Google is trying to give out, let's say 10, right? So we can give out 10 such words to the user. So that is how a simple search autocomplete system works, right? And what will be the time complexity? Time complexity will be O of n into L, n being the number of words at which point we began searching, and L being the average length of words, right? Because there can be many words like this. On average, we can estimate it like this. So it is the number of words into the length of the words, right? So at this point, you must already be getting the doubt that English dictionary has many hundreds of thousands of words. So if we bring out hundreds of thousands of words per search, that is going to be a very expensive operation, and you would be right? So how do we optimize this? How do we bring down this complexity even lower so that we can reply in instant time, right? So let's see how we can optimize. So the way we're going to do it is we're going to add another thing to our try node called top keywords, k being the number of words that you want to return. Let's say if we want to return top 10 words, we're going to have a size of 10 here, k being 10, right? So what we'll do is at every node, at every level, we're going to have already computed list of words that have been updated frequently, right? So let's say I have the prefix CA, and at the node A, I already have a list of computed values which will have top keywords. So when do we do this? At every insert and update, we are going to update the try structure using a upward recursive pattern, right? Let's say there is a new word called cab that has been inserted here, and I want to update this A list. I'm going to check whether there is a new entry to this. So there's already a car, already a cat, which is having a frequency of 7,5, and there's a new cab here which will have naturally a frequency of 1, and let's say if somebody is searching for it, we'll have it at 2, right? So this cab will not fit into this because my top k in this case is 2. So I just want to return 2 words, let's say, and I'm maintaining all these at every level. So when we have the top k as 2 and somebody is inserting cab, there is no need to update it. But when the frequency is increasing for cab, let's say more people are searching for it and this has become 10 now. Now there is a need to update this list. So instead of car comma cat, this will become cab comma car. So for every insert and update, we're going to climb up this tree and we're going to update the list of top keywords that are applicable for that level, right? So the update and insert operations become computationally little expensive, but our search becomes instant. Now, when we want to get words with the prefix of CA, we already have that at the level of A. So we reach A, we get the list, and we return it to the user. And this now becomes an instant or constant time operation, right? So this is how we can optimize, and that is how we can see instant results when we are searching in Google or Amazon or anywhere else, right? So what will be the time complexity now? The search time complexity will become constant, but the update time complexity becomes O of L times log k, and L being the length of the word being updated, and log k if we are using min heap as a data structure instead of a simple list. If you are using an array, it becomes O of k, k being the number of words we are trying to capture, right? So min heap is a good data structure to use here because it gives us log k time complexity. If you don't know what is min heap and how it works, definitely check out my min heap video under data structures playlist, right? So that's all we need to know about tries, guys. It is a fantastic data structure for autocomplete in search. If you have any doubts, definitely let me know in the comments below, and stay tuned for the code implementations. I will see you in the next one. Please leave a like if you found this helpful. Please subscribe if you haven't done already. I'll see you in the next one. Cheers.